Section 2.3, calculating limits using the limit laws. Now, in the previous sections, we've used our tables, right? Just crunching numbers on the calculator and some graphical observations to approximate, or like we said, we're making our best guess estimate as far as the value of the limit, right? But of course, we need to be a little more accurate. Now, this is kind of the next step in the process. This is still not going to be the one size fits all approach, but it does give us some more tools that we can use to evaluate limits. I always say, evaluating a limit or looking to find the value of a limit, table of values, that's always your choice of last resort. So if nothing else works, I can't determine what the limit is either by using some of these tools that we're going to look at or even using a graph, then we use a table of values, right? So that's kind of your method of last resort. But using the limit laws, that still, even in itself, is a little bit cumbersome. I'll kind of give you the breakdown of how this works, but we still, even from here, have to be a little bit more efficient, or maybe a lot more efficient, right? But this is the next step in the process. But again, it's also going to help to understand exactly how limits are evaluated. I mean, that's you still have to keep that in mind as the kind of what's working in the background here, that you want to make sure you have a good understanding of what the concept is all about, so that when we employ shorter, simpler, quicker processes, we still have that basic understanding of exactly what the heck it is that we're trying to calculate or evaluate, right? So take this for what it's worth. It's just the next step in the process, right? You crawl, then you walk, then eventually we'll start running, right? So let's take that. Let's continue to pay our dues to a certain degree. But the limit laws, for the most part, I think these are pretty intuitive as far as what they are saying. So we'll just go through these, and then I'll do a couple of examples where we actually employ them, and then we'll maybe make life a little bit easier for ourselves. So the limit laws suppose, that's our little suppose symbol, that C is a constant, and that the limit as x approaches a of f of x and the limit as x approaches a of g of x both exist. Then according to the limit laws, the first four deal really with just the basic operations. The limit of f of x plus g of x is equal to the limit of f of x plus the limit of g of x, right? So basically the limit of a sum is equal to the sum of the limits. And similarly, 2, 3, and 4, we have the limit of a difference being equal to the difference of the limits. The limit of a product is equal to the product of the limits. And the limit of a quotient is equal to the quotient of the limits, right? Provided, of course, that the limit and the denominator is not equal to 0, as always. So those are just dealing with the basic operation. And essentially what those will allow you to do in evaluating the limit of a function, it basically allows you to evaluate the limit term by term. So whether you have a product or a sum or a difference or a product or a quotient, right, you can evaluate each of those limits individually and then combine them to get the overall limit. Number 5, we make use of quite a bit to say that the limit of a constant times a function is equal to that constant times the limit. So oftentimes it may just be a bit easier if we have a constant value times our function to go ahead and pull that constant factor out and then evaluate the remaining limit, and then just simply multiply by the constant. Number 6, we have the limit as x approaches a of a function raised to a power being equivalent to the limit of that function raised to the power, right? So if I have a function raised to a power, I can evaluate its limit by evaluating the limit of the base, if you wish, and then raising that value to whatever the exponent is. There is a limitation, provided n is an element of, that's the symbol for the positive integers, kind of looks like a z, but that's the symbol that we use in math to represent the integers, so z plus is the positive integers. Number 7, this is one that comes up quite often. The limit of a constant is a constant, all right, as x approaches a. And again, you kind of think about that. If our x is approaching some a value, but our function is a constant function, what does that mean? Well, it means that the value of the function never changes, all right? Remember, a constant function, that's a graph, it's a horizontal line. The value of the function never changes, so I don't care what x is doing or what x is approaching, the value of that function is always the same. So do keep in mind the limit of a constant is a constant, or is the constant, and that never changes. The limit as x approaches a of x is a. Right? If x is approaching a, then the value of x, the limit of x, would be whatever that a value is. Right? So as x approaches a. Number 9, similar to number 6, instead of the function we have the variable. We've got the limit as x approaches a of x to the nth power being equal to a to the nth power. Provided again that n is a positive integer. And the reason for that, a lot of that has to do with the evaluation of roots and that type of thing. But with integers, we want to raise them to positive powers. Okay. Number 10. Again, very similar to the power rule, but where we bring in those radicals. Remember, radicals can be written as exponents as well. But this is where really especially the value of the index plays a part, because we want to avoid complex or non-real numbers. So the limit as x approaches a of the nth root of x is equal to the nth root of a. And the limit as x approaches a, number 11, of the nth root of f of x is equal to the nth root of that limit. Both of those provided that the index is an element of the positive integers. And if n is even, then our radicand must be positive, right? And that's to avoid the complex numbers. So we are restricting these indexes, we're restricting these exponents to be positive integers, right? For these rules to apply. But I think most of these probably should be pretty intuitive. It almost looks like all you're doing eventually is you're just plugging in the a value in place of x. Right, and that's essentially what ends up happening. Right? We're going to talk more in detail on that as we go through. But those are your limit laws. And so that, again, it's another tool that we can use to evaluate some limits. Right? Being able to maybe break it down into smaller parts or smaller steps. Instead of looking at the overall limit, I can break it up into these smaller pieces and evaluate these simpler limits and then just combine the results. Right? So just some kind of simple examples. This next set of examples really just more for illustration, not typically something we would be running into, but kind of shows how these limit laws work. So for example, given that we have the limit as x approaches a of f of x equal to -2, limit as x approaches a of g of x equal to 5, limit as x approaches a of h of x equal to 0, without even knowing what those functions are, what a is, irrelevant, we have the values of each of those limits. Evaluating each of the following limits. Finding the limit as x approaches a of f of x plus g of x, right? And so the idea here is to make use of the limit laws to where I can rewrite each of those limits in terms of the values that we know. So in other words, limit as x approaches a of f of x plus g of x can be rewritten as the limit of f of x plus the limit of g of x, right? The limit of a sum is equal to the sum of the limits, because each of those we know. We know that the limit as x approaches a of f of x is -2. We know the limit as x approaches a of g of x is 5. So now I can take each of those, and it's really just substitution now. Plugging in -2 in place of that first limit and 5 in the place of the second. And I've got -2 plus 5, or 3. All right, and it may be tempting just to say, well, okay, well, why don't I just plug -2 in right here and 3 in right there? Well, essentially, yeah, that's what happens eventually. But remember our purpose here. Like I said, sometimes you have to remember the reason, why do you practice before you play the game kind of thing. You want to get all the fundamentals down. You want to make sure we're understanding why we're doing what we're doing when game time comes. So yeah, that's kind of essentially what ends up happening. But this is an illustration of how we can use the limit laws, right, to rewrite these. And so it's another tool that you have for evaluating limits. The second one, B, finding the limit as x approaches a of the fourth root of g of x. And so we had a couple of limit laws that allowed us to evaluate roots. So this one giving us the limit of the fourth root of g of x. We said in terms of evaluating a limit of a radical, we can simply evaluate the radical of the limit, right? So in other words, these two statements are equivalent to each other. So the limit of the fourth root of g of x is equivalent to the fourth root of the limit of g of x, Right? And again, the limit of g of x as x approaches a, we know, is 5, and I get the 4th root of 5. Right? So notice the substitutions that I'm making, I'm not plugging in the numbers in place of the functions. I'm plugging the numbers in place of the limits. Right? So I plug -2 in place of the limit as x approaches a of f of x. I plug in 5 in place of the limit as x approaches a of g of x. Right? So it's not a substitution in place of the function, it's a substitution in place of the limit. C, limit as x approaches a of f of x over h of x. So we did have a limit law that said the limit of a quotient, limit as x approaches a of a quotient, is equal to the quotient of the limits. Right? And again, those are then two limit values that we know. Limit as x approaches a of f of x is -2, limit as x approaches a of h of x is 0. And now I've got 2 over 0, which is an undefined fraction, right? So that limit ultimately then is undefined. Right? For the same reason that any fraction whose denominator is 0 is undefined. Now, so for an example with a specific function, right, evaluating a limit using the limit laws, right? Now again, this is paying your dues. Like we said before, you gotta grind it out and pay your dues before you're able to, use all of the simpler and more efficient processes. So if asked to evaluate a limit using the limit laws, then that's exactly what we need to do, break this thing down using our limit laws. So I just have a couple of examples with that. The first one, at the limit as x approaches 2 of that function 5x squared minus 3x plus 7. And so it's using the limit laws to break this thing up into its minute pieces until eventually I can evaluate each of the limits. So there's a limit of a difference and a sum. The first step, I went ahead and broke it up into the sum and difference of the limits. In the second step, I made use of that constant multiple rule, right? The limit as x approaches 2 of 5x squared would be equal to 5 times the limit as x approaches 2 of x squared. The limit as x approaches 2 of 3x is 3 times the limit as x approaches 2 of x. And the last one I just left alone. It's the limit of 7 as x approaches 2. There's no constant multiple rule there. But then we're able to evaluate each of those limits because we did have a property limit law that said the limit as x approaches a of x to a power is simply equal to that a value raised to the power. All right, so the limit as x approaches 2 of x squared is equal to 2 squared times the constant 5 in front of it. And similarly, the limit as x approaches 2 of x is 2. Again, just plugging in the a value 3 times that value. And then the last one, like I said, don't forget this guy. It pops up a lot. The limit as x approaches 2 of 7, right? That's the limit of a constant, is the constant. I don't care what the a value is because a constant function always has the same value. I don't care what your x value is approaching. And then from there, now we're just doing the calculation, right? So 2 squared is 4 times 5 is 20, minus 6 is 14, plus 7 is 21, and that's the value of the limit. But that's how you break it down using the limit laws. And certainly you can do maybe a little consolidation of steps. I'm not going to beat you to death with having you do a bunch of limits using limit laws, because this is still kind of a time-consuming process. You have to do a lot of rewriting and all, but we're going to look at a much more straightforward way to do this here in a second. But yeah, I mean that's breaking it down using the limit laws. You could maybe consolidate some of those steps, but yeah, that's how it works. The second one even a little bit more involved because of the fraction, but here's a step-by-step breakdown, right? Here's use of the limit laws. So I've got the limit of a quotient. Limit as x approaches -1 of that function. And one of our limit laws said the limit of a quotient is equal to the quotient of the limits. So that's the first thing I did. I went ahead and broke it up into the quotient of the limits. And now essentially each of those, the numerator and denominator, is going to follow the same process as what we had with the previous example, right? So I went ahead and broke the numerator up into the sum and difference of the limits. Same thing with the denominator. And then I applied the constant multiple law where that applied. So with the limit as x approaches -1 of 2x squared being 2 times the limit as x approaches negative 1 of x squared. And similarly with the limit as x approaches negative 1 of 3x, that would be 3 times the limit as x approaches negative 1 of x. So that step is application of the constant multiple rule. That's probably where, if you wanted to combine these into one statement, that would be fine, instead of having to rewrite that twice. But it's all about getting it to eventually the point to where you can evaluate each of those little individual limits according to our limit laws. And then I'm just plugging negative 1. Right? The limit as x approaches negative 1 of x cubed is negative 1 cubed. The limit as x approaches negative 1 of x squared is negative 1 squared. And then the limit of a constant is a constant, right? So the limit as x approaches negative 1 of 1 is 1. Again, on the denominator, the limit of the constant 5 is 5. And then 3 times the limit as x approaches negative 1 of x is negative 1. And then once we plug everything in, then it's just calculation from there. You do end up with 0 in the numerator divided by 8, which is 0. So I would say all of that work for nothing. Right? 0 is our final value for that limit. Right? But that's an illustration of how we use the limit laws. Again, it's still a cumbersome process, time-consuming process, but it's our next logical step in the process, right? But what I want you to notice, and this is what you probably already kind of mentioned before, I could have gotten the same values for those limits if I'd have just plugged in that a value from the beginning. All right, so when we said the limit as x approaches 2 of 5x squared minus 3x plus 7, notice eventually what happens at the end of this thing, all you end up doing is plugging in 2 in place of x anyway, right? So why not just do that from the beginning and save ourselves a lot of work and a lot of heartache, right? So yeah, I get the same value, 21. You plug in 2, I've got 2 squared is 4 times 5 is 20 minus 6 is 14 plus 7 is 21. And the same thing happens down here, all right? Because notice eventually, again, that's what happens in that last step anyway. You end up plugging negative 1 in place of x, right? So just do that from the beginning. And you will again get 0. You can check me on that if you don't believe me. Negative 1 cubed is negative 1. Negative 1 squared is 1. So I've got negative 1 plus 2 is 1. 1 minus 1 is 0. And then 5 minus 3 times negative 1 would be 5 plus 3 or 8. 0 over 8 is 0. Right? So fortunately, instead of having to go through the limit laws, right, every single time, we have this process that is called direct substitution. Direct substitution property or the substitution rule or something to that effect. I just call it direct substitution. Now at this point we're just talking about polynomial and rational functions. Certainly, this is going to apply really to any type of function that we deal with, but for now these are the only two that we've kind of talked about. So we'll extend this as necessary as we address other types of functions. But in general, the direct substitution property says that if f is a polynomial or rational function, and your a value is in the domain of f, and that's really the important statement here, right? If I have a function and I'm evaluating that function, the limit of that function as x approaches some a value, as long as the a value is in the domain of your function, then the limit as x approaches a of f of x is simply equal to f of a. Now, in other words, I can just plug that a value into my function, and I can use that to evaluate the limit. All right? These functions are called continuous at a. That's a term that we are going to talk about a lot. We have a whole section devoted to this idea of continuity, or what does it mean for a function to be continuous, either at a specific point or across an interval. And continuity plays a big role, plays a large part in a lot of the concepts that we're going to talk about as it relates to calculus and derivatives and so forth. So this kind of introduces this idea of continuity. If a function is continuous at a, then I can evaluate the limit as x approaches a by using direct substitution. But more generally, for our purposes at this point, as long as that a value is in the domain of our function, then I can evaluate our function using direct substitution, provided it's polynomial are rational at this point. And again, we'll expand that as we get into other types of functions. Now, that's all great, fine, and wonderful. Direct substitution as long as the a value is in the domain of our function. Well, what happens if it's not? Right? So if we look at, say, for example, the limit as x approaches 4 of x squared minus 4x over x squared minus 3x minus 4. Direct substitution is not going to work here because if you plug 4 into that function, if you plug 4 into that denominator, you've got 4 squared is 16, minus 3 times 4 is 12. So that would be 16 minus 12 or 4. 4 minus 4 is 0. So the denominator there is 0, so that tells me that 4 is not in the domain of that function. Also notice if you plug it in the numerator, you would get 4 squared is 16, minus 4 times 4 is 16. You would get 0 there also. So you actually end up with 0 in the numerator and the denominator. That's, again, a discussion for a little bit later. The main observation, though, at this point is direct substitution can't work, will not work, because 4 is not in the domain of the function. I mean, you can't evaluate the fraction. It's undefined. Okay? But wait. Here's the part I'm really interested in. Notice that we can rewrite that function by factoring that numerator and denominator and actually end up with x minus 4 as a factor in both the numerator and denominator that I can then divide out, leaving me with x over x plus 1, which that can be evaluated for x equals 4. Now, why can I use this to evaluate that first or original limit? Now remember, when we were evaluating limits originally, one of the statements we kept saying was, the limit as x approaches a of f of x. I don't care what happens at a. All I care about is what's happening as we approach a, all right, or as x approaches a. So what happens at a is irrelevant. And we even made the statement, we said we don't even need a to be in the domain of our function in order to evaluate the limit. So here's what's happening here. By taking this function and simplifying it, you are writing this function into an equivalent form that is equivalent to the original function everywhere except where x equals 4. Because notice, the only thing that I'm eliminating from this thing is x minus 4, that factor. So I'm taking 4, or that particular factor, out of the function. I no longer have the issue with x equals 4 being or causing an undefined fraction, because the factor that was causing the issue, x minus 4, in that denominator is no longer there. So my denominator is no longer 0, and I can actually then evaluate this new function, which is equivalent to the original function everywhere except where x equals 4. And since that's the one point I don't care about, right? I don't care about x equals 4, then I can evaluate this limit of this new function equivalently to the limit of the original function. Okay? So it's all based upon the fact that when you're evaluating the limit, I don't care what happens at the a value. It's all about what happens as we're approaching the a value. And if I can rewrite my function, here's the bottom line. If I can rewrite my function into a form that is equivalent to the original function everywhere except at that point in question, which is our a value, then I can evaluate the limit equivalently. And so in this case, I can use direct substitution now, and I've got 4 over 4 plus 1, or 4/5. There's the value of our limit. Okay. Keep this in mind. Here's kind of the trick behind the process. If I have a function, or if I have a limit that I am looking to evaluate that is undefined at our a value, so in this case undefined at x equals 4, my objective will be to rewrite that function into an equivalent form. I'm not going to say simplify it, because that's not exactly true in every case, It's more about rewriting the function into an equivalent form that is equivalent to our original function everywhere except at that point in question, at the a value. And then you can use your direct substitution to evaluate, if possible. Okay? But notice how is that going to happen? Well, I have to be able to get rid of whatever's causing that denominator to be 0. So in other words, when we looked at this original function and I was able to factor it here, I had that factor of x minus 4. That's what's causing that denominator to be 0. Because when you plug in 4, you've got 4 minus 4 is 0. So if I can eliminate that factor, then I no longer have an undefined fraction, and I can use direct substitution to evaluate it. Right? So that's kind of the underlying process here with each of these examples that I'm showing you here. Now, what I'm doing is I'm giving you some different looks. It always looks perfectly fine when we do it here. As we know, every function is different, every problem is different, so each one is going to have their own little twists and turns or tweaks that we have to make to it. But what I'm showing you is the bottom line process and what's happening in order to accomplish our objective, which is to evaluate the limit by direct substitution. All right, so I'm going to come back to this other one after I give you the theorem. So that's the use of this theorem, or this theorem that I'm giving you. Very important theorem. If f of x is equal to g of x, whenever x is not equal to a, then the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x. Of course, provided the limit exists. I mean, if the limit doesn't exist, the limit doesn't exist. All right, but if I'm able to evaluate g of x, and g of x is equivalent to f of x everywhere except at x equals a, then the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x. But essentially, again, what that is saying is if I can come up with an equivalent form for my function, and I can use direct substitution to evaluate the limit there, then it's exactly the same value as the limit of the original function. This next example is kind of a specific little case. It's a special case, but I want to show you how this works. It's another tool for the toolbox. And I always talk about, you want to put as many tools in the toolbox as you can. All right? Now, the only problem is you have to remember what tools you have in the toolbox. And you have to be able to find those tools when you need them. All right? So that's a couple of the issues there. You also want to make sure you practice using the tools as much as you can. We don't want the tools to get rusty and we can't use them. So that's where all the practice comes in. You want to make sure you practice using all these different techniques that we're talking about, so that should the need ever arise, I can recognize when I need it, when I can use it, and then I can pull it out of my toolbox and use it when necessary. So this next example is kind of a specific case, right? So if you remember from algebra, you talk about, and even in trig, we talk about this, rationalizing denominators, where you have maybe you end up with a radical in your denominator, a square root in the denominator, and you rationalize the denominator by multiplying by the square root. You can rationalize denominators, you can rationalize numerators. I mean, it's all about manipulation of the function, taking a function and writing it into a different form or an equivalent form by just manipulating it. Right? And we end up doing this quite a bit in different situations, right? Not even with just limits, but other things that we're going to be working with, where putting my function into a different form makes it easier to apply a certain process or technique or perform a certain type of calculation. Okay, so it's not always just about things being undefined or evaluating a limit. It just may have to do with putting a function into a different form that makes it easier to work with that function. Okay, so these are all just different techniques and tools that we can use to do that. So I'm looking at this limit as h approaches 0. Now the square root of 1 plus h minus 1 over h. Okay. Now here again, notice we're evaluating the limit as h approaches 0. We can't use direct substitution because 0 is not in the domain of that function. All right. So I need to rewrite this function. Well, it's not like the previous one where I could just factor something and divide the h out. But that is still my objective. What's causing the problem in the denominator? The fact that there's an h in that denominator, and I just can't plug 0 there because I end up with an undefined fraction. So somehow I need to rewrite this function that allows me to eliminate or get rid of that factor of h in the denominator. And in this case, that can be done if we multiply the numerator and the denominator by the conjugate of that numerator. Remember the idea of a conjugate? Separated by the sum and difference. So square root of 1 plus h minus 1. Square root of 1 plus h plus 1. Those are conjugates, radical conjugates in this case, or irrational conjugates we call them. But notice, of course, I have to multiply the numerator and denominator by the same thing. So ultimately what you're doing is you're rewriting this original function by multiplying that fraction by 1. All right? It's a fancy one, but as long as the numerator and denominator get multiplied by the same thing, I'm multiplying by 1. And we are choosing 1 to be written in a specific way, so that notice what happens. So it's kind of, with a lot of this stuff, the ends justifies the means. It's like, well, why are you doing that? Because look what happens if I do, that kind of thing. So notice what happens if we multiply. Now, make sure we multiply this correctly. This is where the algebra stuff comes in. I'm multiplying the sum and difference of the same two terms. I'm going to get the difference of squares. I mean, that's a basic polynomial type process. Sum and difference, product of the sum and difference, or product of conjugates, gives me the difference of squares. So I'm going to square the square root, square root of 1 plus h times square root of 1 plus h, leaves me with 1 plus h. If you go through your whole FOIL method, you end up subtracting out the two middle terms. So we square the first term. The first term in this case is the square root. Square root of 1 plus h squared leaves me with 1 plus h. And then 1 squared is 1. So there's our difference of squares. But you have to make sure that gets multiplied out properly, of course. Otherwise, it's not going to work. Now, don't force this stuff. I mean, you know what the result needs to be. And sometimes that's a hindrance. Because I know what it needs to be, I take for granted that I've written things correctly when maybe I haven't. So you want to make sure that it actually does work the way it's supposed to work. Don't take it for granted, because if you wrote something wrong, it's going to throw off the rest of it from that point forward. I just can't presume. So make sure that it actually does work. Now the denominator is h times the square root of 1 plus h plus 1. All right. So that's just a product. And I'm leaving it as a factored form because, again, what do I want to happen? My objective here is to get rid of that h. So I don't want to multiply that out, because I would then have to turn around and factor the h out. So leave it in factored form. Simplify the numerator. Notice 1 plus h minus 1 just leaves me with h. So that gets me down to this point. And now notice I can divide out that h. I have a factor of h here. I have a factor of h there. Now, dividing out the h in the numerator, don't forget I'm left with a 1, and then the denominator now is square root of 1 plus h plus 1. But notice now I can use direct substitution. I can plug that 0 now into that expression, and I get 1/2. That's the value of the limit. Okay? So with respect to that problem, it's a specific process. It's a specific tool. This idea of rationalizing the numerator, multiplying by a conjugate, that type of thing. A couple of other things I want to mention just in general with respect to evaluating limits while I'm looking at this. Notice that in each step of the process, in the first one that we did and in the second one that we did, and we went through these processes of rewriting our function, notice that I included that limit statement every single step of the way. All right. So in other words, the limit as h approaches 0 of this is equal to the limit as h approaches 0 of this is equal to the limit as h approaches 0 of that, and so on. In other words, I keep that limit statement until I do what? Until I actually plug the value into our function, until I actually perform the direct substitution. That may seem like a little technical issue, but without this limit statement, look, if you drop that statement out, those two statements are not equivalent to each other. This and this are not equivalent to each other. All right, because the first statement is a limit statement. That's the limit as h equals 0 of all that stuff is not just equal to that function. All right. So make sure you are including your limit statement every single step of the way until you actually evaluate the limit. And then once you make your substitution, right, once we plug our a value into our function, then we can drop the limit. Now we're doing the calculation, and we show the value of the limit. All right, now I'll remind you that as we go through this stuff, because it's not a minor deal. It's a big deal, and I will dock you for that. You leave off your limit statement, I will dock you. Now this last one is kind of another special case, but I do want to show you an example with one of these. Now, limit laws also hold for one-sided limits, right? So I'm going to keep that in mind as well. And then I want to show you this other example. So whether you're evaluating a one-sided limit or a whole limit, the limit laws apply. Direct substitution applies, So if I can use direct substitution with a one-sided limit, then I could do that. The only thing to be careful of, and we'll see examples of this going forward, is to make sure again that the value that you're plugging in is actually in the domain of the function. And for a one-sided limit, make sure it is in the domain of that one side of your function. And again, that's something I'll have to talk a little bit more as we go through. But bottom line, limit laws also apply for one-sided limits. I mean, there's no difference there. You can use direct substitution as well. Just be careful of domain. So again, we'll look at some examples. But I want to show you this next example just because it's kind of a special case, and it's a tricky little situation. But again, some algebra stuff that I want to mention to you as well. So finding the limit as x approaches 4 of the absolute value of 4 minus x over 4. Okay. Let me do that. Okay. Now, notice, of course, if I plug 4 into that thing, it is undefined, right? 4 minus 4 is 0. I have an undefined fraction. Also, I do get 0 into the numerator as well. But bottom line is, I can't just use direct substitution there because it is an undefined fraction. Okay? So the question then becomes, can I rewrite this function into an equivalent form so that I can use direct substitution, or get it into a form that I can somehow evaluate the limit? And sometimes using the left and right hand limit is the route to go, is the path to take. Right? Because when we talked about one-sided limits initially, I said, look, sometimes you can't evaluate the overall limit, but you can look at the limits coming from the left and from the right to see if those are the same. And if those are the same, then we can evaluate the overall limit. And if they're not the same, we can at least tell you that the overall limit does not exist. But here's what I want you to notice in this case. I've got this limit at x approaches 4. So I'm going to break this into the left and right hand limit. Let's look at the limit as x approaches 4 from the left. Well, that's not. Okay. Which means I'm plugging in values for 4, or values for x that are smaller than 4, right? They're less than 4. We're coming at 4 from the left side. So if we were to do a chart, let's say, we would do numbers like 3.9, 3.99, that kind of thing. But regardless, whatever value you're plugging in place of x here is going to be smaller than 4. So I know that that denominator, 4 minus whatever, is going to leave me with a positive number, because 4 is always going to be larger than the number you're plugging in. The numerator is also 4 minus x, but it's the absolute value. Well, what does the absolute value do? The absolute value just means that the numerator is always going to be positive. Right? So regardless of whatever 4 minus x is, the absolute value in that numerator is going to make this thing positive up here all the time. Now, in this case, it ends up being the same number, right? I mean, if you plug in, say, 3.9 in place of x, then I've got 0.1 in the denominator. I've also got 0.1 in the numerator. And they're both going to be the same. As long as you are plugging in values of x that are less than 4, you're going to get exactly the same value in the numerator and the denominator. So in other words, what I'm doing in the next step is making use of that, or taking advantage of that observation. And here I don't need the absolute value, because I'm going to get exactly the same positive number in the denominator that I'm going to get in the numerator. So I'm able to eliminate the absolute value here, but it's simply based upon an observation that those two numbers are going to be the same. As long as you are plugging in, and I should have a negative on that, our little symbol, as long as you are plugging in, what happened with these as well, but as long as I'm plugging in values for x that are less than 4. But now look what I have. Now I have a fraction that I can simplify, because 4 minus x and 4 minus x, those are exactly the same. And I can simplify that to 1. Now notice, that's now the limit as x approaches 4 from the left of 1, because that is straightforward simplification of this fraction. And now I'm evaluating the limit of a constant, and the limit of the constant is the constant, right? And I get 1. The right side is maybe even a little bit trickier. Maybe get rid of some of this. Yeah, it's getting rid of more than what I want, but give me a second. I want to get rid of that. That's what I'm after. Let me go back and put these. I'm OCD with that. All right. The right side limit. Limit as x approaches 4 from the right, right, of our absolute value of 4 minus x over 4 minus x. Now, notice in this case, if we plug in values of x that are larger than 4, because we're coming at 4 from the right side, so we're looking at numbers like 4.1, 4.01, etc. This denominator is always going to be a negative number, right? Because the x values are larger than 4. So I don't care what you plug in there, it's always going to give me a negative number. Now, the numerator, the 4 minus x up here, is going to give me the same number that I get in the denominator, that same negative number. But the absolute value makes it positive. Okay. So I get the same number in the numerator as I get in the denominator, but the denominator is going to be negative, the numerator is going to be positive because of the absolute value. So I'm not getting the same number this time. What I'm getting is an opposite. And this is where, we're big boys and girls now. Don't associate this little symbol right here with necessarily meaning negative. The more general use for that symbol is to indicate opposite. And so in other words, writing what I have here, 4 minus x, we already said this is going to be a negative number. The numerator is going to be positive, but the relationship between that numerator and that denominator is that they are opposites of each other, right? That's a little bit tricky, so you've got to be careful with that, but it all goes back to just basic understanding of the notation, right? So don't always associate that little symbol with a negative number. Maybe it is, maybe it isn't, especially when you have variables flying around, right? So I tend to use that, I call that the opposite. So whatever I get in the numerator, it's going to be the opposite of whatever I get in the denominator, because it's the same number, the denominator is negative, the numerator is a positive number. But the main result of that, though, then, is I'm able now to divide out this 4 minus x. Right? Because that's still 4 minus, that's just 4 minus x now. I've gotten rid of the absolute value. But instead of being left with 1, as we were in the previous, the left-hand limit, we're left with negative 1. And then that, again, is the limit of a constant, which is a constant. Again, there should be a plus on that. Okay? So it's a tricky little problem. Right? So I want you to make sure you take a look at this one and see if we can digest that and understand what's going on right there. All right? That makes a good test question, something like that. So there's the evaluation of the left-hand limit and the right-hand limit. Now, ultimately, the original limit was the entire limit as x approaches 4, which we can now say does not exist. But why does it not exist? Because the limit as x approaches 4 from the left is not equal to the limit as x approaches 4 from the right. So there's an example of how you can show that a limit does not exist. All right, I don't really have any other way to rewrite that function. I mean, there's nothing else really that you can do with absolute value. So we did this based upon observation of what happens if we look at the left hand versus the right hand limit and what happens to the values of that expression. All right. So I can evaluate either one individually or look at the entire limit, which I now can say does not exist. Okay. Now, these next couple of theorems again, I think the theorems themselves seem pretty intuitive as far as what they're saying. The problem, though, as I find with these, it's not what the theorems say, it's the execution of them, or kind of knowing when to use them, I guess. So the first theorem says that if I have functions f of x and g of x, where if f of x is less than or equal to g of x, when x is near a, right? So as x approaches a, I have this function f of x that's always smaller than the function g of x, or less than the function g of x. All right, as usual, except possibly at a, because we don't care about a. And if both of the limits of f and g as x approaches a exist, then I could say that the limit as x approaches a of f of x would have to be less than or equal to the limit as x approaches a of g of x. Okay? So again, think about what that says. That should seem pretty intuitive. That should make sense, right? So if I have this function f of x that's always smaller than this function g of x, less than or equal to in this case, when we're near a, then the limit as x approaches a of f of x would have to be less than or equal to the limit as x approaches a of g of x, right? Because the function values for f are always smaller than the function values of g near a. Hopefully that makes sense. Taking it a step further, we'll look at what's called the squeeze theorem. Squeeze theorem is a pretty cool little theorem when you see how it works. But the problem with the squeeze theorem is recognizing how to use it. That's the problem with this guy. So it's an interesting little theorem, and we're going to see it pop up on occasion where we can make use of it. Right? So I do want to talk about it. But I get that with this one, it's a little bit difficult to recognize when you can use it. So it's a tool that goes in the toolbox, but it's sometimes when you look at that tool, it's like, well, when do I use that? Right? When do I know how to use that thing? So I'll give you an example with it here, and we'll see another one come up later. So what the squeeze theorem says is, and again, I think it should be pretty intuitive. It should make sense as far as what this is saying. It's similar to what we had in the previous. If now I'm looking at three functions, f, g, and h, where our function g of x is trapped between the functions f and h. And so if f is less than g is less than h when x is near a. Right, so as x approaches a, f of x is less than or equal to g of x is less than or equal to. So g is trapped between f and h, except possibly at a, which again we don't care about a. If we also know that the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x, those two limits are the same, so those two functions are approaching the same value as x approaches a. Whatever that value is, call it L, then the limit as x approaches a of g of x also has to be L. Because remember, g is trapped between f and h, so wherever f and h go, g's stuck. It has to go to the same place. It has to approach the same number. It has no choice as x approaches a. Okay? Again, that should be pretty obvious. It should be a pretty straightforward idea. The problem is, how do I execute it? It's like maybe like a little graphical thing here. Let's say I have this function f, right, that's approaching some number. And let's say I have this function h that's approaching some number. Right, so here's our a value. Here would be, say, the L value. Call that f, call that h, right? So as x approaches a, f and h are both approaching that same value. Now let's say we have this function g that's stuck between f and h, right? And I'm telling, okay, g always has to be between f and h. Whatever g is doing, all right, when we're approaching a, I know g is stuck between those two. So it has no choice but to also approach L as x approaches a, right? That's the squeeze theorem. It looks more like a y, make it a g, okay? So that's how the squeeze theorem works. So g is squeezed between f and h. The first example is kind of, a basic little generic example, but it illustrates how this works and how we can use it. So if I have this expression, I've got 2x is less than or equal to some function g of x. We don't even know what g is less than or equal to x to the fourth minus x squared plus 2 for all x in this case. And we're looking to evaluate the limit as x approaches 1 of g of x. Well, in this case, since I know g of x is trapped between those other two functions, if you look at the limit as x approaches 1 of 2x, now I can use direct substitution there, right? Plug in 1, I've got 2 times 1 or 2, so there's the limit as x approaches 1. Likewise, the limit as x approaches 1 of our function on the right side, plug in 1, you've got 1 to the 4th is 1, minus 1 squared is 1, so that's 0, plus 2 is 2. So since the limit as x approaches 1 of the function on the left is equal to the limit as x approaches 1 of the function on the right, and since g of x is trapped between those two functions, then it has no choice. The limit as x approaches 1 of g of x also has to be 2. These little 3 dots right here, that's the symbol that we use for therefore. So I would say, therefore, the limit as x approaches 1 of g of x has to also equal 2 by the squeeze theorem. Okay? That's basically how squeeze theorem works. Here's another example. This one is a show or prove. You remember your proofs from trig, right? Where we're trying to prove statements are true. So here's a show statement. Show that the limit as x approaches 0 of that expression, square root of x cubed plus x squared times the sine of pi over x is equal to 0. Okay. Now, you can't use a product rule here, because I could say maybe, okay, we'll have a limit of a product right there. I have the limit of that square root times that sine function. So how about we break that up as a product and use a limit law? Well, the problem is that limit as x approaches 0, the sine of pi over x doesn't exist, right? I can't plug 0 into that expression. It's undefined. Okay? So direct substitution doesn't work. Product rule doesn't work. Okay? And you should have seen maybe some examples of this in your homework as far as an observation when you were doing some of those tables in the previous section, I believe it is. But here's a case where we can rely upon some other pre-existing information. Right? All those tools in the toolbox from trig. We have algebra tools and trig tools. Here we're using a basic algebra tool. Remember from trig, the sine function has a range of -1 to 1. Why do we harp on domain and range of trig functions so much? So that when we get to calculus, we know what they are. We've got a sine function whose value is always between -1 and 1. That's the range of the sine function. I don't care what your argument is, pi over x in this case. I don't care. The sine function, by definition, by rule, has a range of -1 to 1. So then that gives me an inequality statement that I know to be true. So then what we do in this next step is consider, well, let's just multiply all parts of that inequality by the square root of x cubed plus x squared. All right? So you multiply this, and this, and this, right? Each piece of that inequality by the square root of x cubed plus x squared. I could do that. That's a basic algebra technique. I can multiply both sides, or in this case, all 3 parts of an inequality by the same value. As long as it's a positive value, it doesn't change my inequality. And since it's a square root, that's a positive value. So if that statement is true, then this statement also has to be true, because we're just multiplying each piece by some positive number. It doesn't change the inequality. Now, if you look at the limit as x approaches 0 of f of x, I'm calling that's this piece. As x approaches 0, if you plug in 0 into that expression, you're going to get 0. Likewise on this side, call this our h of x. And you plug in 0, you're going to get 0. All right? And since both of those limits as x approaches 0 are 0, and we know that this is trapped between those two, well, that's our original function. That's our square root of x cubed plus x squared times sine of pi over x. It has no choice but to also approach 0 as x approaches 0. Okay? So there's my summary statement. Again, I don't want to say that the function is approaching 0 without that limit statement. So by the squeeze theorem, we can say that the limit as x approaches 0 of g of x, that function in the middle, also has to be 0, because each of those functions on the outside, as x approaches 0, those are approaching 0. That's a classic squeeze theorem, right? But it all starts with first being able to come up with a comparison of your original function. This is the trick with squeeze theorem. I have to be able to compare my original function to two functions whose limits I can evaluate. Right? I have to show that that function falls between two functions whose limits I can evaluate, and those limits have to be the same, right? Because if the one on the left and the one on the right were approaching two different values, if those were not both 0, then I couldn't guarantee you that the one in the middle approaches 0, right? Yeah, so that's a tough little example. I mean, I understand that, and understanding squeeze theorem. Squeeze theorem is not the problem; it's the execution of it. But keep that in your back pocket. We're gonna see that pop up again at some point. Okay? Otherwise, I think that is it for that section. Yep, section 2.3.